Hi, my name is Dylan Powell, and this is my spontaneous lecture for the second turn-in for fluid mechanics. So one thing that's always been really cool to me is how airfoils and airflow are used in airplanes, especially in very high-efficient craft like solar-powered, like the solar-powered airplane that was able to fly because it had a very high lift force while having a very low drag force. So as you can see, this kind of represents how air flows, or any fluid really, flows around certain obstructions. So here we have a plate wall. You can obviously see there's a lot of turbulence behind it, which leads to pressure drag. There's also a lot of viscous drag around these areas of turbulence. And then when we move to a sphere, we get about half the resistance because there's a little bit of a contraction there, which reduces the pressure drag. And then when we add this fin to the back, it reduces it even further down to 15. And then when we have this full airfoil shape, we have about a 20th of the resistance of this flat plane due to the fact that the streams are easily split, and then there's almost functionally no low pressure zone for pressure drag to come into play. And the viscous drag is very low. It's only really between this no slope boundary condition and the fluids directly around it. The V infinity forces are, the V infinity is very close to where the surface is moving through the air.
So there are two very important properties of porous media. One is the porosity and one is the permeability. So when we find the porosity is you get a little container, we call that the top volume, and then you fill it with your porous media, say gravel in this case, and then all you need to do is pour liquid into this container until it reaches the top volume. And the porosity is simply the volume of liquid divided by the total volume. And now permeability is a little bit different. It depends on porosity, but it's also dependent on like the shape of the pores and the size of the particles. So in our class, we just assumed that all the pores were perfect cylinders and that the particles were perfect spheres. So something can have a very high porosity, but it can have a very low permeability if the particles are too big to actually exit from the pores and flow through the material. And one way we can use permeability is by Darcy's law. And Darcy's law is proportional to the porosity, or the epsilon value, which we can calculate this way, cubed divided by 1 minus epsilon squared. So what you get, and we know that epsilon only goes from 0 to 1, and the permeability is proportional to this. So what we get is, starting at 0, we go up and reach an asymptote. So one thing we must assume is that the epsilon value is small enough so that the permeability does not reach infinity, basically.